Okay, this problem is extremely challenging, so I put it in a category of its own. Problem 32 says if the least common multiple of the first 130 positive integers, so 1, 2, 3, 4, all the way up to 130, is divided by the least common multiple of the first 125 positive integers, the quotient is which of these numbers? There's no way in the amount of time you have to actually calculate the least common multiple of these huge sets of numbers. You have to recognize that when we're doing common multiples, any common prime factors, remember when we sorted prime factors into Venn diagrams, the common prime factors went in the intersection and weren't counted twice. So the idea here is, let's just solve a simpler problem. Let's do the quotient of the first 8 positive multiples and the first 4 positive multiples. And then let's look at the prime factorization. 1 is just 1. I shouldn't use equals. 1, prime factorization is 1. That isn't even prime, so, but it is one of the 125 positive integers. It's going to be irrelevant to the problem because, dividing by 1 isn't going to change anything. The prime factorization of 2 is 2. The prime factorization of 3 is 3. The prime factorization of 4 is 2 multiplied by 2. 5 will be 5. 6 is 2 multiplied by 3. 7 is 7. And 8 is 2 of 2 of 2. So when we're, how do I say this? When we're looking at this quotient, we're really just looking at, for the ones that are greater than 4, that are not in the denominator, which of them have prime factors that are not already accounted for in the ones in the denominator, because the ones that are accounted for would be in the intersection and they would factor out. So the things that would be the prime factors that have not yet been used would be 5, certainly. A 2 and a 3 have already shown up here. 7 has not. The tricky thing here, and it also applies to the actual problem 32, is while there are 2's that have shown up in the first 4 positive integers, we haven't yet seen 3 2's. And so there would be another 2 here that wouldn't factor out. So the quotient would be 5 times 7 is 35 times 2 is 70. So 70 would be the quotient of the least common multiple of the first 8 positive integers and the least common multiple of the first 4 positive integers. Well, that isn't the problem we're solving, but I just use that to illustrate how you would solve the problem we're solving. In other words, you don't have to concern yourself with the first 125, other than just to keep in mind, which of the prime factors that we're about to reveal for the next 5 of these numbers have already been used. For example, 126 is 2 of 63. 63 is 9 times 7, so 3 times 3 times 7. So there's the prime factorization of 126. All of these will have shown up because we have 2's, we have 9, we have 7 in these previous 125. So this is going to add nothing to the quotient. 127 is itself prime, so that will be part of the quotient. Here's the tricky part, and here's why I missed this problem. I thought 127 was the answer choice A. But 128 is 2 64's, 64 is 2 32's, 32 is 2 16's, 16 is 2 8's, 8 is 2 4's, 4 is 2 2's. So you have 1, 2, 3, 4, 5, 6, 7. 128 is 2 to the 7th power. In these first 125 positive integers, you get as high as 2 to the 6th power for 64, but not any higher than that. So one of these 2's will not factor out, a single one. 129 is not divisible by 2, but 9 plus 2 plus 1 is 12, and so it's divisible by 3. It's 3 multiplied by 43. 43 is prime, but it's accounted for in this first 125 positive integers, and so is 3. So this adds nothing to the quotient. 130 is 2 multiplied by 65. So that's 2 of 5 of 13. So those would all be in the first 125, so that doesn't add anything. So 127 times 2 is the quotient, which is answer choice B, 254. That's a hard problem. But when I say it's a hard problem, but here's the thing, and this is why we're practicing. It's a hard problem if you haven't dealt with this concept in this format before, or it's not the right way to say it. I suspect, actually I know at this point, that this idea comes up again and again in math competition problems, because Dr. Patel talked to me about a problem recently where this same idea comes up. So if you start to see these same ideas again and again in math competitions, you just get better and better at recognizing these type of problems, and you just get more and more efficient at solving them. So hopefully that will help.